Welcome to the lecture 4.1. Today we're going to discuss about the probability mass functions, cumulative distribution functions, expected values. So I put here the variance, but I don't think that we'll be able to cover the variance as well. So could you please tell me what is the probability mass function, which we discussed last time? So probability mass function. What is the probability mass function? Okay, so it's simply a function, right, which can be written as a table or as a graph. Is going to tell us the probabilities of every output of your random variable, right? So if your random variable, for example, takes the 6 values from 1 to the 6, then this table is going to show us the probabilities for every single output. So the probability mass function can be written as the table, or sometimes it can be written as the graph as well. So graphically, it is even more descriptive because it describes us now how this probability, which is 100%, is distributed over the variables, over the outputs. So we know that every probability mass function should fulfill two properties. One is every probability is always between 0 and 1. And the second property is the sum of all of the probabilities is equal to the 1, right? So we consider that for our experiment, the sum of all of the probabilities is 100%. And this graph is essentially going to show us how this 100% is distributed over this 6 outputs. You can see here that on the x-axis, I've got 6 outputs of this particular random variable. And this graph is going to show us how this is distributed over the 6 outputs. So that is why this kind of graph is called as the distribution of the random variable. Could you please write it down? Distribution of the random variable. And so when the distribution of the random variable is shown using this type of the graph, where we have used the bars, is called as histogram of the PMF. Like Instagram, but histogram, okay? Histogram of the PMF. So histogram is the type of the graph, okay? So we can show the distribution of the random variables differently. And one of the ways of showing this distribution is called the histogram. So histogram is the type of the graph where we are going to use the bars. So higher the probability, the higher the bar. So this bar graph, so this histogram is very important because if you look to the distribution of the random variables and if you just connect all of these bars, you're going to have this bell-shaped curve, so which we call as the normal distribution in the continuous case. Normal distribution in a continuous case. In the discrete case, we're going to call it a binomial distribution. Well, we are going to talk about the binomial distribution in more details. Let's say at this stage, you should just know that this type of the graph is called a bell-shaped curve. It is very important for us. Well, if you would just show the graph of the PMF in the graph, in the 2D graph, what you would get here is just simply 6 points, right? So if I say for this random variable, what is the probability that x is equal to the 2? 0.15, right? What is the probability that x is equal to the 4? 0.25. What is the probability that x is equal to the 8? 0. What is the probability that x is equal to the 2.5? 0, right? For any other values which are not indicated here, the probability simply is going to be equal to the 6. So in terms of the functions, this function is very limited. It has the values for only 6 points. And we can't really just make the assumptions, or we can just really go into the continuous case where we have infinitely many values for the functions with using the PMF because it has limited values. It has the values for only 6 points. So we need to figure out how we can connect the continuous case with the discrete case. And it appears one of these functions is going to be called as the cumulative distribution function. So here it is. So cumulative distribution function is the probability that the random variable is smaller or equal to a certain value. Well, the PMF is going to tell us what is the probability of your random variable takes a particular point, right? A particular value. So we know what is the probability that x is equal to the 3 from this table. What is the probability that x is equal to the 3? 0.25. Or you can also know what is the probability that x is between 1 and 3. What is the probability that x is between 1 and 3? That is going to be 0.25 plus 0.25, 0.5, right? So it is simply the sum of the p of x is equal to the 1, 2, and 3. Okay? You just need to sum this. Okay? So this table, what does this tells to you? And this f of x is going to tell you what is the probability until certain point. F of 1 in this case, for example, is simply 0.1, but f of 2 here is going to be equal to the 0.25, the sum of the two values until the 2. F of 3 is going to be the sum of the 3 probabilities, okay? So sum of all of the probabilities until 3. Or f of 4 is going to be the sum of all of the probabilities until 4 and so on. So in order to construct this, it is going to be not so difficult to construct this. So we just need to sum all of the probabilities up to that certain point. F of 6, for example, is going to be equal to the 1 because in this case, we're going to sum all of the values. Okay? So the f of x is going to be equal to the sum of all of these values. F of 5 is the sum of all of these values. F of 4 is going to be equal to the sum of all of these values, and so on. Okay? Well, it appears the cumulative distribution function, I hope that you understand the word cumulative, right? So cumulative is kind of like accumulation, right? So the summation of the probabilities, okay? So, well, here we're going to sum all of the probabilities up to a certain point. It has many applications, and one of the applications is that it is possible to write down the discrete probabilities in the continuous case. So let's try to sketch the graph of the PMF, then CDF. Okay, what is a PMF? Probability mass function, and CDF is a cumulative distribution function. Okay, so I'm going to put the values here. It's going to be 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. And here I'm going to put the probabilities. It's going to be 0 0.2, 0 0.4, 0 0.6, 0 0.8, and 1. Could you please? So let's try to sketch PMF first of all. What is the probability that x is equal to the 1? Do you remember this table? So, sorry, I don't have this table here. But if you remember, it was 0 0.1, right? So probability that x is equal to the 2 was 0 0.15, right? 0 0.15. Probability that x is equal to the 3 is 0 0.25. X is equal to the 4 is 0 0.25. X is equal to the 5 is 15. Then x is equal to the 6 is 0 0.1 again. Okay? This is the graph of the probability mass function. It's always going to look like this, just the points. And if you would like to find the probability of x is equal to the 5.1 or 4.9 or 3.5, it is simply going to be equal to the 0. Everywhere except the 6 points, your probability mass function simply equals to the 0. Okay? So now let's try to sketch the graph of the CDF. So for all of the values between 1 and 2, the cumulative distribution function is going to be 0 0.1. Okay, something like this. So if I just looked at this table, if I say, what is the f of 1? What is f of 1 from this table? 0 0.1. But what is the f of 1.5? Do you remember what is this by the definition? It is the probability that your random variable is smaller or equal than 1.5, which is going to be equal to the 0 0.1 because you're going to sum all of the probabilities smaller than 1.5, right? But if I would just put 1.7, you would still get 0 0.1. Or 1.99, you would still get 0 0.1. You understand this? So till the 2, for any values, I'm going to get 0 0.1. So from 2 to the 3, I'm going to get the different values. From 2 to the 3, it is going to be 0 0.25. From 3 to the 4, it is going to be equal to the 0 0.5. From 4 to the 5, it is going to be 0 0.75. From 5 to the 6, it is going to be 0 0.9. And from 6 to infinity, it is simply going to be equal to the 1. This is the graph of the CDF. Because, for example, if I say, what is the f of 7? You're going to tell me this is 1. F of 9 is 1. F of 11 is 1, right? So for any value greater than 6, the cumulative distribution function simply equals to the 1. So this is important property. So for example, if I say what is the f of 8, it is going to be the sum of all of the probabilities from 1 to the 6 plus 7 plus 8, right? This is by the definition. But we know that the t probability is simply equal to the 0, and the sum of all of these probabilities is equal to the 1. So that is why the f is equal to the 1 for any value greater than the 6. Okay? So can you see the differences in the graph between the PMF and the CDF, the probability mass function and the cumulative distribution function? So the cumulative distribution function is piecewise continuous function. It has infinitely many values, okay? Of course, it is like a piecewise, it is defined as a piecewise, it is not fully continuous, but it has finite number of the discontinuities, if you know what I mean, okay? So you can count the number of the discontinuities of this function. Well, here, this function is just a point function. It is the super discontinuous function, the PMF. It has defined it only in the 6 points only. Okay, so later on, when we are going to define the functions for the continuous variables, we would need the CDF in order to make the connection between this. Okay. So another reason why we need to learn about the PMF, CDF, sorry, the cumulative distribution function, is that it allows us to find the probabilities in the intervals without knowing the probability mass function. Okay, so let me write down f of b. So the f of b is probability that your random variable is smaller than the b. For example, if I say here, what is the probability of cumulative probability of the 4? It is going to be the probability that x is less or equal to the 4, right? And at the same time, I can know what is the probability of f of t. It is going to be the probability that your random variable is smaller than the t. Well, if I would like to know what is the probability that your random variable x is between the 2 and 4, I can either simply subtract these two cumulative functions or cumulative values in order to find this probability. So if I would like to know what is the probability of x between 2 and 4, it is simply going to be the subtraction of the f of 2 from the f of 4. It is super important. It is like really important. You need to write this down. So here, so the probability of x is between 2 and 4. It is going to be, what is the f of b, by the way? Could you please tell me what is the f of b? It is p of x, p of 1 plus p of 2 plus p of 3 plus p of 4, right? It is the sum of all of the probabilities from 1 to the 4. And what is going to be p of 2? F of 2, sorry, f of 2. It is going to be the sum of all of the probabilities until 2, right? P of 1 plus P of 2. And obviously, you are going to subtract, and what you get here is simply P of 3 plus P of 4. And this is what we want to define, right? If you would like to find the probability in some interval between A and B, where A is not included and B is included, then you can find this using the cumulative distribution function. This is especially very useful in the continuous case, where in practice most of the time, we're going to have the CDF rather than the PMF, okay? In practice most of the time, we're going to have the cumulative distribution function in our hands rather than the probability mass functions, okay? So in this case, this is how we're going to extract the probabilities of a certain values or in some intervals from the cumulative distribution function. Okay, so let's do a small example or a small exercise. So suppose that a PMF of a random variable is given like this. So when your random variable x is equal to the k, then its probability is going to be simply equal to the 1 over 2 in the power of k. Well, what you need to do is you need to find, first of all, the CDF, the cumulative distribution function. And then you need to find the probability that your random variable x is going to be between 2 and 5. Okay? So first of all, before we proceed, I would like to ask you a couple of questions. Like, is it a proper probability mass function? Yeah, so the sum should be equal to the 1, right? It is like the two conditions only. So your probability should be always between 0 and 1, and it is clear that it is always between 0 and 1, right? Because no matter what is the k, It is going to be 1 over reciprocal of the 2 in the power of, right, k, which is simply between 0 and 1 always. But is it the sum is equal to the 1? Yes, I mean it is 1, right? Because this is actually the geometric series, right? So let us do this. So the sum of, um, let's do this, I from 1 to the k of 1 over 2i. Okay, it is going to be equal to the 1 over 2 plus 1 over 4 plus 1 over 8 plus 1 over 16 plus and so on, right? So do you remember we call this function as geometric series, right? So when every next term is obtained by multiplying the previous term to one number, we call this as a common quotient, right? So here the common quotient is equal to what? What is a common quotient? 1 over 2, right? Because your first term, b1, is equal to the 1 over 2. The second term is obtained by multiplying b1 to the cube. The third term is obtained by multiplying b2 to the cube, and so on. Okay? So we know that there are certain formulas for some of the geometric series. For example, this can be geometric series or any other series when you're going to obtain the next term by multiplying the previous one to the common quotient is also a geometric series. For example, you can write it like a 1 plus 2 plus 4 plus 8 plus 16 plus and so on. It's also a geometric series, right? So where the common quotient is going to be equal to the 2. Do you remember what is the sum of the k terms, the first k terms of the geometric series? The formula is b1 times to the 1 minus q in the power of k divided to the 1 minus q. So this is going to be the formula to find the first k terms of any geometric series. Okay? So what we need to do is we need to show that the sum of the 2 in the power of k, we need to show that the sum of the 1 over 2 in the power of k goes from 1 to the infinity, is equal to the 1, not to the k. We need to sum not only the first k terms, we need to sum infinitely many terms, right? Where this k, which is the number of the terms, tends to be infinity, tends to go to the infinity, okay? So this q in the power of k tends to go to the 0 when k goes to the infinity if q is less than 1. Okay? So in our case, the k is equal to the 1 over 2, right? So q is equal to the 1 over 2, sorry. So this is equal to the 0 when k goes to the infinity. Do you agree? Yes? So 1 over 2 in the power of k, when k is a huge number, is going to be equal, obviously, to the 0 when k goes to the infinity. Okay? It's super clear, right? So that is why in this formula, we can just neglect this term. Okay? Because this is 1 minus 0, simply, when you're going to sum infinitely many terms. So the sum of all of the values from 1 to the infinity of 1 over 2 in the power of k is going to be equal to the first term divided to the 1 minus q. Okay? The first term is equal to the 1 over 2. Do you remember? The first term starts from the 1 over 2. And the common quotient is also 1 over 2. So that is why it is equal to the 1. So yes, it is a proper density function. Or it is a proper probability mass function. Okay? Cool. So let's find the CDF. So it appears the cumulative distribution function is going to be equal to the 2 to the power of k minus 1 divided to the 2 to the power of k. And it is also easy to show, right? So what is the f of k by its definition? So by the definition, f of k is the probability that your random variable x is smaller or equal to the k, right? Well, we know what is the random variable for every value of the k, right? Okay, so what is f of k is probability of 1, 2, and so on until k, right? It is going to be the summation of, let me write it like 1 over 2 plus 1 over 4 plus and so on plus 1 over 2 to the power of k. And here I have to use the full formula of the geometric series. So it is going to be the first term is 1 over 2 times the 1 minus the quotient in the power of k. It is 1 over 2 in the power of k. divided to 1 minus 1 over 2. 1 minus q. Okay? So then I can cancel these two terms, and what is left is going to be equal to this term if you give the common denominator. Okay? So now I'm going to use this formula, the cumulative distribution function, in order to find the probability of this x in between these two numbers in the interval. So the probability that x is between 2 and 5 is going to be equal to f of 5 minus f of 2. It is going to be equal to, I'm just going to substitute 5 and 2 in this formula. It is going to be 2 to the power of 5 minus 1 divided to the 2 to the power of 5 minus 2 to the power of 2 minus 1 divided to the 2 to the power of 2. So I'm going to give the common denominator 2 to the power of 3 into the next term. It is going to be 2 to the power of 5 minus 1 minus 2 to the power of 5 plus 2 to the power of 3 divided to the 2 to the power of 5, right? And if you simplify the terms out, it is going to be equal to the 7 over 32. Right? Because you can cancel this 2 to the power of 5s. This is going to be 2 to the power of 3, which is 8 minus 1, 7, divided to the 32. Okay? You can do this easier, actually, or differently. So this probability is equal to the probability of x is equal to the 3, 4, and 5, right? We know each of these probabilities. It is equal to the 1 over 8 plus 1 over 16 plus 1 over 32 according to this formula. And if you sum, you're still going to get 7 over 32. Okay? So if your final goal is to find the probability in the interval, of course, there's no much sense to find the CDF first of all, and then use this in order to find the probabilities in the interval, right? Okay, so you can just find the sum of the probabilities. But we are going to see this later on in the practice as well. So for most of the cases, realistic cases, we're going to have rather the CDF, the cumulative distribution function. And it is very useful to use this CDF in order to find the probabilities in the interval without knowing the whole PMF. Okay? Cool. So the next topic which I would like to discuss is the average. Okay? So let's assume that you've got the random variable which takes the two values, only 2 and 4. So let's do an experiment, let's do a game. So we're going to play the game, and the output of this game is always going to be either 2 or 4. And I'm going to just write down all of the outputs of this game. So it's going to be 2, 4, 2, 4, 2, 2, 4, 2, 4, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outputs. Okay? Do you understand this? So you're playing the game. The output of your game is a random variable. It takes only two values with equal probabilities. Probability that in the next time when you play this game, you're going to obtain 2 or 4 are equal. What is the average of all of the results after 10 times you play this game? 3, right? You sum all of the values and divide this to the 10. You sum, right, and divide this to the 10, it is going to be equal to the 3, okay? So you can find the average by just adding these two values and dividing this to the 2. So what is the average of the x? So the average of the x is 2 plus 4 divided to the 2, 3, okay? Average of the x. So now this is nothing to do with the probability at this stage, okay? So if you would like to find, we're talking about the output of your game, okay? You roll a die, right? You can get the numbers 1, 2, 3, 4, 5, 6, okay? If those numbers would make some sense, for example, you're going to sit down this number of the time when you roll a die, right? Then how many times you're going to sit down, do some exercise in average, right? You know what I mean? So in order to find the average, is it okay to just sum all of the outputs and divide this to the 2? Well, in this case, yes, because the weights are the same, right? But in general, no. In general, you would do this differently. For example, if you would have another table where the probabilities are going to be, let me put this. Where the probabilities are going to be 0.2 and 0.8, then this is going to be different, right? So let me give you a small example. Like, let's assume that after all of the exams and final exams, so Alisher has got 60 for his homework, okay, and he's got 40 for his midterm exam and 30 for his final exam. Huh? Which Alisher, right? So one of them. So if I would like to know what is the final grade of Alisher, so what I should do, should I just simply sum the three values and divide this as a three? Should I take its average? You know what I mean? So he's got 60 out of 100 for the homeworks. Maybe you, maybe you. Then 40 for the midterm out of 100 and 30 for the final out of 100. If I would like to calculate the grade, should I just sum the three values and divide this to the three? No, right? Because we know that homeworks is only 20% of the grades, midterm is 40%, and finals 40%. And obviously, it is much more worse to get higher grades in the exams rather than in the homeworks, right? Yes? So the weights of the exams are much more higher than the weight of the homework. And of course, I'm not going to just simply sum the three numbers. I'm going to sum them by weighting to their categories, according to their categories. So I'm going to multiply 60 to the 0.2. 40 is going to be multiplied to the 0.4. Plus 30 is going to be multiplied to the 0.4. If you sum it, it's going to be equal to the 30, right? Is it 30? 1.2. 12 plus 16 plus 12. That is going to be equal to the 24, 40. Right? So I multiply 0.2 to the 60, it is 12. This is 16, this is 12, and if I sum, I've got 40. Okay? 40 is going to be the grade of Alisher. Okay? So this average is called a weighted average. It is not simply the average when we're going to take the sum and divide this to the number of the items, right? We're going to weight every item according to their rate. And the same is here. So if your random variable takes these two values, 2 and 4, with a certain probabilities, then the weighted average of this random variable is going to be 2 times the 0.2. Okay, I'm just going to multiply the random variable to its probability plus 4 times the 0.8, okay? And I'm going to take the sum. And it is going to be equal to the 0.4 plus 3.2. It is going to be equal to the 3.6. So, well, do you remember? If the weights are the same, then the average is 3. But if the weight of the 4 is higher, then the average value is going to be equal to the 3.6. This is called the mean of the random variable. And sometimes we're going to call this as an expected value. It is one of the most important attributes of any random variable. So expected value, where you're going to multiply the random variable, the output, each output to its probability and sum this at the end. Could you please calculate the expected value of this random variable? What is the expected value of this random variable? The expected value of this random variable is going to be equal to the 0.6 plus 2 plus 1.2. It's going to be 3.4. Is it 2? $3.8. Okay. So let us write down the formula for the expected value. So it is going to be the formula. So we are going to consider the random variable and its average, or the weighted average, is going to be calculated using this formula, and it is going to be called as an expected value. So if you've got the random variable, if you would do some experiment many times, then this is what you need to expect. Okay? But talking in a human language, this is simply the weighted average. Okay? We're going to multiply every output of your random variable to its corresponding weight, to its corresponding probability, and then we're going to sum all of these values. So let's do a couple of examples. So let your random variable contain two values, 0 and 1, with the corresponding probabilities. Could you please calculate the expected value of this random variable? Which is not so difficult, right? So the expected value of the x is going to be equal to 0 times to its probability plus 1 times its probability is going to be equal to the 2 over 3. This is the average, okay, weighted average between all of the values between 0 and 1. So let's do some more realistic case. So at the raffle, there are 500 tickets. So let's assume that I would like to issue 500 tickets for Nowruz, and I would like to sell this to you for $1. Okay, and there are 2 winning tickets. One is $100, and the second one is $50. Okay, and if you buy one of the tickets, how much gain you should expect? How much profit you should expect? If you buy one ticket from one ticket, how much profit you should expect from one ticket? Do you understand the question? So yeah, we need to do the weighted average. But first of all, we need to create a table, the probability mass function table for the random variable, which calculates your profit, right? So what kind of profit are possible? So for example, if you win $100 ticket, how much going to be your profit? $99, right? So the probability of winning, of having profit $99 is equal to 1 over 500. Right? Do you understand what's going on? So you buy one ticket, you pay me $1, and then you won $100. Your profit is $99. And probability of having this $99 is 1 over 500 because there are 500 tickets and you should get one of them, right? So if you win $50 ticket, then your profit is going to be equal to the $49, right? Then its probability is also 1 over 500. So if you don't win anything, what is going to be your profit? Minus $1, right? And probability of having this is 498 divided to the 500. Okay? Well, the probability or the expected value of the x, so the average profit you should expect, the profit you should expect is going to be expected value of the x is going to be 99 times its probability plus 49 times its probability minus 1 times its probability. And if you add all of these numbers, it is going to be equal to the minus $0.7 or 70 cents. Okay? Of course, it doesn't make sense. I'm going to read now the conclusion. The conclusion is, if you play this lottery ticket, you should expect to lose 70 cents. Okay? Of course, it doesn't make sense when we're talking about just one game, right? But if you look to the long range, the conclusion is going to look like this. If you play this lottery game a lot of times, you're going to expect to lose 70 cents every time. Okay, from every ticket. This is what does it tell you. So when we're talking about the probabilities and when we are talking about the random variables, it is very important for us to make some predictions. And the expected values are going to help us to make this kind of predictions. Okay? So overall, this course, we're going to see the applications of the expected value. Because the meaning or the calculations of the expected value is pretty much straightforward, right? You're going to always multiply the output to its probability and just sum, okay? But interpretation is more difficult. So so in our next lecture, 4.2, which is going to be online for you, we are going to make some simulations with RStudio. So I would recommend you to watch that lecture, okay? So we're going to make this kind of simulations in order to get the 0.7. So let's try to talk about some properties of the expected values today. So let's make let's reveal some of its properties. So let's say now the random variable is going to be x when you roll a die, the result of rolling a die. Could you please calculate the expected value, please? Well, we first of all can make the table, right? X can take 1, 2, 3, 4, 5, 6. And the probabilities are always 1 over 6. And if you would like to find the expected value of the x is going to be equal to 1 times to the 1 over 6, 2 times to the 1 over 6, 3 times to the 1 over 6, 4 times to the 1 over 6, 5 times to the 1 over 6, 6 times to the 1 over 6. And this is going to be the sum of all of the numbers from 1 to the 6 divided to the 6, right? So what is the sum of all of the numbers from 1 to the 6? It is 7 times to the 6, right? Divided to the 2. 21 divided to the 6. That is 3.5, right? Oh, by the way, I used the algebraic algebraic series in order to find the sum, right? Do you remember the sum of the algebraic series? It is n times the n plus 1 divided to the 2, right? So 6 times the 7 divided to the 2. Cool. Is it clear how to calculate this? So you can give some meanings to this number. For example, let's assume that um, so let's do this like this. So every lecture, I'm going to roll a die, okay? And this result is going to be used to give you some number of the quizzes per week, okay? If there is only one, then you're going to have one quiz per week, two quizzes per week, three quizzes per week, or if it faces to the six quizzes per week, okay? Then this E of X, the expected value of the X means, okay, so how much quizzes you had in average every week, okay? So if you would do this experiment every week, then you would have 3.5 quizzes in average every week. This is what does it mean, this, okay? Let's play next week. He's going to bring the die, and we're going to do this because if there are 6 quizzes, it is terrible for you and for him, not for me. Okay, so let's change the game a little bit. So most often, it is very important for us to calculate the expected value of some function of the random variable. Okay, not the random variable itself. So let's play this game again. I'm going to roll a die. And I'm going to give the result in the square of dollars to Alisher. Or not Alisher, Kamaluddin. Okay? I'm going to roll a die. If the result is 2, I'm going to give him $4. If there is like a 5, I'm going to have $25. Okay? So if I play this game next time, how much money I should give to him? So how much money Kamaluddin should expect to gain? Okay, let's do this together. So I'm going to create the table, right? How much money I should give to him. So money I should give to him. So the profit, let's say, profit. So of Kamaluddin. So he can profit $1 or 4 or 9 or 16 or 25 or 36, right? What is the probability that he's going to earn $1? 1 over 6. Probability that he's going to earn $4 is also 1 over 6. This 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 is also 1 over 6. Probability that he's going to earn $36 is also 1 over 6. Probability that he's going to earn $16 is also 1 over 6, right? Because I'm rolling a die, right? So, and the probability of getting one of these values is always the same because this is the fair die. And then the expected value of the profit is going to be equal to the sum of all of these values multiplied to their corresponding probabilities, right? It is going to be 1 plus 4 plus 9 plus 16 plus 25 plus 36 divided to the 6. Well, this is going to be 20, 30, 55, 91, 91 over 6. Okay, 15.1. So Kamaluddin should expect to have $15.1 if you play this game. Okay? So you see, now could you please derive me the formula? So if you know the x and if you know its probability mass function, can you calculate the expected value of any function of this x? Yes? Right? So in our case, what we did is we just multiplied the x in the square to the probability of the x, right? Probabilities didn't change. We just multiply always to the values of the x into the new function, okay? And this is going to be our formula. So, okay, let's do this in this case. So let's say x can take the 3 values. You need to calculate the expected value of the x in the square, right? So I'm going to do this in this. I'm going to write down x can take values -1, 0, and 1 with the probabilities 0.2, 0.5, 0.3. And then I'm going to create another table for the x in the square. It is going to take the values 1, 0, and 1 with the probability 0.2, 0.5, 0.3. You see, so I'm not changing the probabilities. The values are changing, but the probabilities are not going to be changed. And it is logical, okay? So sometimes it is not obvious, okay? If I wouldn't show you the previous example, it wouldn't be so obvious. But the probabilities won't be changed, Okay, the explanation is that you can get the 0 only when x is 0. And the probability of x is equal to the 0 is 0.5. So that is why the probability of x is equal to the x squared is equal to the 0 is also 0.5. Okay? Then the expected value of the x and a square, the expected value of the x and a square is equal to 0.2 plus 0.5, which is 0.5. By the way, the expected value of the x is going to be equal to 0.1. Okay? So in general, we can write down the formula like this. So if you've got the random variable x, then the expected value of some function g of x is equal to every time you're going to calculate the function's value and multiply this to the probability of the x itself. Okay? So just having this formula, we are going to calculate the probability of the a times the x plus b, where a and b are the two constants. Okay, so our new function is going to be ax plus b, linear function of the random variable. And let's calculate this. So it is very important because it reveals how the expected values are going to behave when you are going to multiply some constant to your random variable or when you're going to add some constant to your random variable. Okay, so let's do this. So the expected value of the ax plus b is going to be equal to, according to the previous formula which we just wrote down, it is equal to the summation of, I'm going to calculate I goes from 1 to the k, let's say. It is going to be axi plus b, and this is multiplied to the p of xi. Right? Do you remember this? So if it would be x, okay, so let me write this. If it would be not ax plus b, but if it would be like a x in the square, what we did before, what we did is you squared the x and multiplied this to its probability. This is what we did before. Do you remember? You multiplied, for example, 1 in the square to 1 over 6, 2 in the square to 1 over 6, 3 in the square 1 over 6, and so on, right? And we're doing the same thing here. Okay? And now I'm just going to open the brackets up. So if you open all of the brackets, what you get is the summation of axi p of xi plus the summation of b of p of xi. Then you can take out this a from the brackets, and you are going to have the a times the summation of the xi p of xi, plus if you take out the b from the brackets, you're going to have simply the sum of all of the probabilities. So could you please tell me what is the summation of the x times the p of x and summation of all of these values? No. E of x, right? A times the e of x plus b, because this is 1. The sum of all of the probabilities is 1, but the sum of all of the probabilities multiplied to their corresponding values is equal to the expected value. Okay? So if you would like to find the expected value of the ax plus b, it appears, so you can apply the expected value linearly for all of these terms. Okay? Then, when you're going to find the expected value of a constant, it is going to be simply equal to the constant. Okay? And the expected value of a constant times your random variable is going to be, this constant is going to be taken out. So this is important formula because we're going to work with this formula a lot. Okay? So now let's try to understand why the expected value of a constant is a constant. Can you try to explain me why the expected value of a constant is a constant? Or let's say, for example, the expected value of the 2 is equal to the 2. So what does it mean, this expected value of the 2? It means that you're doing the experiment, right? And your experiment is going to give your result always 2. Let's do your experiment 10 times. How many 2's you're going to have? 10. 2, 2, 2, 2, 2, 2, 2, 2, 2. What is going to be average? 2. Okay? So this is the meaning of this. The expected value of a constant is equal to the constant because you're always going to have a constant in your probability experiment. And obviously, the average is also a constant. Okay? So in our next lectures, we're going to talk about the variance. So you should watch the lectures before coming to the next one. Okay? Thank you.